Hello, everybody. Welcome to today's row. And it's a great honor for me to introduce today's speaker, Ronnie Ben-Tal. I think he actually doesn't need an introduction. He's quite well known in the area of optimization and also in the area of robust optimization. He's one of the founding father of robust optimization. He is the emeritus professor at Technion University. And he has won so many prizes so far. One of them is a Hachian Prize for Lifetime Achievement in the area of optimization. And I actually remember the presentation he had, which included a poem, which was quite nice there. So word cannot express how grateful we are for having you today, Ronnie. And without further ado, I would like to ask you to start the presentation. So thank you again, and the mic and the screen is yours.
Thank you very much, Reza. Now, the talk is from a recent paper which was published in the journal, Informed Journal for Computing, not the last issue, the one before. But this work that I'm presenting also triggered a lot of interesting papers we are working with, and here are two representatives, Wolfram and Aras are working with me on extending this idea. So the title is kind of controversial. I want to maximize. What does the minimum add to the fact if you want to maximize? Well, it turns out that this is a crucial question, and the answer is the basis of the algorithm. So we are talking about maximizing a convex function, MCF in short. So we are going to assume about F, about the feasible set. Usually we'll assume in this talk that there are twice continuous differentiable, and also the constraint set, and the set is a compact set, so solution exists and so forth. Under all these assumptions, still the problem is known to be NP-hard, and this was already proved in 1974 by Swart. So, but what I claim, and as you see in this talk, that this is an NP-hard non-convex problem, but still it's structurable in a way that practically we can solve such problem even in large dimension with many constraints and many variables and so forth. So there is something special about this non-convex function, that you maximize a convex function. That's bad because we would like to minimize the convex function. But still, it's a non-convex function with a special feature that I will mention during the talk that enable us to do that. So here is a list of applications, and there are many applications already in the early 80s and 90s. There were big survey papers about maximizing a convex function with a very long list of papers. But since then, even today, this is a very common problem people encounter in many applications, including in the new data science business and all that. But of course, as you can imagine, my interest in this came from robust optimization. Let's talk about the first stage. If you have a problem which has uncertainty, and somehow you got a solution, either from history or with the algorithm that you have, and now you realize that there might be perturbation P, uncertainty in the parameters, and you want to be sure that the constraints is still satisfied for the solution you found, for every possible value of the uncertain parameter in the uncertainty set. So you want to maximize age on P of the function age of X and P, and see if it's still less than or equal to 0. This is the first stage in applying robust optimization. You have a current solution, maybe it's already immune against uncertainty. If you solve this problem and it's still less than or equal to 0, then you're sure that your solution is immune against perturbation P in the uncertainty set U. Now, normally, the full problem in the objective function is you minimize on X, you maximize on P, age of X and P. Okay, that's the full robust optimization procedure. Now, since you want to minimize on X, it's tractable when the age is convex in the variable X. But what happens if the perturbation is an additive one? This is what is called in robust optimization implementation error. You solve the problem, the computer gave you a very exact solution, X star, but what you can build is not as accurate as X star. Maybe you have a small error when you actually execute X star. The example already in our book on robust optimization. So in this case, if age is convex in X star, in X, then it automatically also convex in P. And we want to maximize the convex function on P. So in our private history of that, I mean, mainly Arkady Negroski and myself, we said in the very beginning, in the first paper in MOR on robust optimization, we say we want a method to treat uncertainty that will be tractable. Namely, can solve problem with large dimension and also constrained and so forth. So for that, minimizing on X star need convexity, and this is happening in many problems like linear, conic quadratic, semi-definite, and so forth. So that's fine. But we know how to do it for maximizing on P if P is concave, because we want to maximize on P. But now, if age is convex in X, it's also convex in P. So we have to maximize the convex function. This is the problem I'm talking about. And that was the source. And the classical example already in our book, in our first paper, was antenna design problem. So you want to design an antenna that will concentrate all so your antenna is right here. You want to omit energy or accept an energy in a very narrow area near 90%. So you want all the energy to be here. You want the energy next to the 90%, but still close to be bounded. And you want very minimal loss of energy to the side lobes, these two sides here. So this was the solution of the problem that actually we have to solve actually this problem here, which is actually a linear programming problem. And that gave a very perfect solution to what we want. All the energy concentrated here. But now the engineer take the solution from our optimization problem, which was solved to the accuracy of 10 to the minus 6. But what he can implement, because he has to build an XXI, you have to build an amplifier. And the way that he builds the amplifier is not that exact. There is a small error, which is stays, this row here is 10 to the minus 3, say. So the actually antenna that he builds with the status one, instead of this one, the ideal one is this one. Complete nonsense. So, So it's very important to be able to maximize age on P, even if P is not concave, age is not concave, it's convex. And this is exactly the problem we are dealing with today. So it's a major thing to complete kind of the promise that we have at the beginning, that we can also solve problem with implementation error, in spite of the fact that you have to maximize a convex function, which is an NP-hard problem. Okay, now most algorithms for that kind of a non-convex problem, the very simple one is what is called gradient ascent. Since we're maximizing, I'm talking about ascent and not descent, which goes back even to the Frank-Wolf thing. So we will maximize this linear function subject to the constraint set. And the basic theorem talks about when, where does such an algorithm under certain condition converge to only, not even to necessarily to a local minimum, but to just to one that satisfies the gradient inequality. But if you look at the first statement in the proof of this theorem, it says the sequence of points generated by this classical algorithm is monotonically increasing to the solution. That's good, fine, we want to maximize. But on the other end, look at the first stage of the algorithm. Let x0 be an initial value. Who is this initial value? And without saying anything about the initial value, and the iteration are monotone. So look, for example, at this picture here. So that's a convex function that you want to maximize. If your starting point at any point to the left on this side of the minimum, because of the good property of monotonicity, you will be converging to this point, which is not the global maximum. The global maximum is on the other side. So all the starting point from this side will lead you not to the global optimum. We'll see that the algorithm that we will talk about actually will find an initial point that will lead you to the global optimum. So the quality of the final solution is fully dependent on initialization. So all the effort in the algorithm I'm going to present is going to be what we call the phase one, how to find X point X0, from which you use the phase two, which is the classical gradient ascent algorithm. And we are not looking at something more sophisticated because what we claim that if the starting point is already very good approximation of the starting point, this algorithm will converge very, very fast. And there's no need to be very sophisticated here. Okay, but let me explain the philosophy or what was my idea at the beginning about maximizing a convex function. And why we need something new, cannot use just the usual calculus. So traditionally, I'll just read this part. Traditionally, condition under which a feasible solution X star of problem P is identified as optimal are based on the body of knowledge in mathematics covered by infinitesimal calculus. If we cite from that paper I mentioned here, the basic idea of the calculus is analyze function by means of their behavior on a micro level. So that immediately explains why calculus doesn't give you an absolutely necessary and sufficient condition for global solution. This global is not a micro property, it's a global property. Consequently, infinitesimal calculus does not provide global optimality condition for non-convex problems, such as problem P we are dealing with. Thus, something new is needed in order to identify X star as a global maximizer, not coming just from calculus, such as the Kuhn-Tucker condition and so forth. What we offer is an intuitively appealing global optimality condition for the problem of a maximizer convex function. And notice, this is not a mathematical statement. It's in quotation mark, but that's the idea. The global maximizer X star problem P is the furthest feasible point from the minimizer of problem P. Yeah, if you are in a deep valley and you want to get to the highest point, you better get away from the minimum as far as you can. Of course, the thing far by what measure? And this is, so we use this condition for designing an algorithm for solving a problem P. But before, we have to explain the following. First, we need a distance measure by which to choose the distance, the furthest point from the minimal point. We elect to use the second order Taylor approximation at the global minimum. I will explain this shortly, as it captures both the notion of difference as well as the function-specific characteristic, such as the gradient and Hessian of the minimum. Okay, but this will be explained. Second, the minimizer of P must be computed. This, however, is a tractable problem for minimizers. So this is the unique feature of the max of convex function. The fact that the minimum is easy to compute. Yeah, interior point method, or polynomial even. If you take any other almost non-convex problem other than the max of convex, that might have several minimum, local minimum, local maximum, to find the global maximum is, or the global minimum is not easier to find than the global maximum. But in our case of the maximum of convex function, the maximum is difficult, but the minimum is easy. Without this, we couldn't have an algorithm. So you might think sometimes people say you lost a coin, you're going and look for it under where there is a good light. Which might not, but in our case, you will see why the minimum point is important. And I could do nothing if this principle, if I couldn't have a good algorithm to solve the minimum of a convex function, but we do. The third thing is the further the point itself is not taken as, so we are looking for the furthest point. We claim that this will be our starting point for the second phase algorithm. But we don't claim that what we find is the global maximum, just a starting point, a good candidate to be a starting point for the simple gradient ascent algorithm or any other naive algorithm that you use to find local minimum. Okay. So the basic step of the algorithm are the following. Compute the minimizer X star of the maximum convex function problem, the minimum. This is the convex optimization problem, and as such is tractable. Approximate the convex F by a quadratic around the minimal point. Okay, we'll talk about it, how and which is the quadratic. Maximize the quadratic over ellipsoid to find x0. So the next thing is we approximate the feasible set, which is general given by a set of convex inequalities. We approximate it by ellipsoid or maybe by another thing. We'll come to that. In this case, we'll have a quadratic objective function and a quadratic constraint, that's the ellipsoid. And then we can use what is known as hidden convexity. hidden convexity, I don't know if you can see what I read, that's the title of the paper that I had with Mark Teboul, called Hidden Convexities for Some Non-Convex Quadratically Constrained Quadratic Problem. To minimize a quadratic subject to a quadratic, even none of them is positive definite. It can be converted in some sense, exact sense, to a convex optimization problem, and that's what is called hidden convexity. I will come to this because this is a main step in the algorithm. So, what is the idea? We want, we have a starting point X star, and we want to make X star, want to maximize f of x minus f of x star. We're maximizing only f. But this immediately suggests to write as an approximation the Taylor around the point x star. Okay, so this is the second order Taylor. It's a quadratic function because our function, remember, is convex. So this is the Hessian is positive definite. So this is kind of a distance function of x from x star. Indeed, the square root of a quadratic term like this is a distance function. So we want to distance ourselves from x star, whatever it is. And we are rather suspect that it would be better to take x star to be the minimum. Why the minimum? It's the first term. The first, okay, so this is good. We maximize this, this is good. We kind of get away from x star. We increase, we get better and better values of x we are seeking. But we want at least the first term to be at least non-negative, so we don't get something smaller. Now, when is this term, the linear term, is bigger or equal to 0 for any x in the convex feasible set? It's exactly the minimum point. The minimum point, the necessary and sufficient for the minimum point is exactly that this term will be bigger or equal to 0 for any x feasible. So this is why we choose the x minimum, to be the one that will be distance from, to be distant from in order to make the right-hand side as maximum, as large as we can. And in this way, we get an approximation to the maximum point away from the minimum point. So this is the rationale, why the minimum point? And it comes actually from calculus. So again, notice that if our solution of the problem is at the point x star, which is the gradient is 0, then we are left only with the distance function. And then we maximize it in order to get the global solution. Otherwise, what we maximize is this second order Taylor around the minimum point. And this is the quadratic. Okay. If you look back now at this picture, the distance point from x star in terms of the usual Euclidean distance is the one on the left, and that will lead us to this global maximum. But this function was built in such a way that the Hessian on the left-hand side is 1 and the Hessian on the right-hand side is 7. So if you maximize, if go from here and you maximize on this side, then the Hessian distance is the largest at this point, which is the global max. Okay, so a maximum at the furthest point is intuitively appearing and give us the need to maximize a quadratic function, but it's still a convex quadratic function that we have to maximize. It's still a hard problem. Well, the next thing is to approximate x by an ellipsoid or something tractable other than that. If it's an ellipsoid, we'll have to maximize a quadratic function subject to a quadratic inequality. Ellipsoid can be expressed by quadratic inequality. And that comes to the hidden convexity business. So the problem that we look at is this one, or more generally. Let me increase this size. Okay. So now in the situation that you write the minimum, but that is just minus the maximum. It's the same because we don't claim anyway that D is positive semi-definite. Okay. So we have a quadratic. Now, what I'm talking now is how to solve this quadratic subject to quadratic. One well-known is to convert it by using the so-called F lemma to convert it to a semi-definite programming, which is a convex problem, tractable, but not tractable, not practically tractable. If we want to solve a problem with 100 constraints and several hundred variables and so forth, then we still have difficulties to solve such problem. So in a paper with Dick, who is here in the audience somewhere, what we suggest is to first diagonalize simultaneously both the matrix D and the matrix A. The first question, and it's an algebraic question, when can two positive, indefinite, when two indefinite quadratic terms, symmetric quadratic terms, can be commonly diagonalized by a matrix, say S. So that SAS will be a diagonal matrix with the alpha in the diagonal, and SDX will be another diagonal. And one condition is that it's enough that one of the function, the quadratic function, will be positive definite. So it's enough that, for example, that A will be, and since we assume that the approximate, so the feasible set is convex, and we approximate by a convex by an ellipsoid, which is a convex, which has a convex function, positive definite A, the sufficient condition for existence of H diagonalizing both D and A holds here automatically. There are even weaker conditions, but it's enough that the constraint will be approximated by a non-degenerate ellipse. In this case, we diagonalize. So after diagonalizing, we have a separable objective function and constraint. Here they are, okay? So you see the coefficient are the alphas in the objective function and the betas and the deltas in the constraints. Okay. Okay, but this is fine. This is convex, and but this is still not convex. The fact that they diagonalize it, some of the terms might have a negative coefficient. In which case, this is not a convex function. We still have to minimize a non-convex function or maximize a convex function. So the question is, how can we still solve this non-convex function? So the first step, any variable xi square, I define a new variable yi. Okay, so that's what we did. We just substitute for each of a square term a new variable I, and we write what we use, that yi is xy square. So this is a bad non-convex constraint. So this is still a non-convex problem. But we do what we think we can do. We use the inequality. you might be disappointed because how do I know that the solution of this will be a solution of that? But that's what hidden convexity does, and in a constructive way, and this is in the paper by Digdan Hertog and myself. And actually what we claim in the theorem is the following. If you solve this problem, you find an X and a Y, and maybe some of the constraint will be will not satisfy the equality. But then our theorem says that in this case, you can convert that point to another point, X star and Y, that will satisfy all the constraints in this problem with equality, in which case it will be a solution. And this is given by an explicit formula. Here is the theorem. So if you solve the problem and there are some excess, if all of them are equal to yi, then we are finished. But if there are some constraints that are not satisfied, and they generate such an X star, Y star with some inequalities, then you take the X star and you compute this new X variable that was violating the equality. And here is the formula for it. Everything in the right-hand side is known. And so that's the new X, and that's the new Y. And of course, now equality holds for the X. And we can solve that you remain feasible and you remain with the same objective function as in the original X bar. This is, by the way, if you use the S lemma to convert to a semi-definite problem, you don't get such a strong result. It's only after you diagonalize. And this is done constructively in the proof. So this means we know how to solve the problem of maximizing a convex subfunction subject after we use the second order Taylor extension, and we use a quadratic approximation of the constraint. Namely, we know how to approximate the feasible set. Here it's a polyhedral one, but just for the example, with an ellipsoid. And there are several ways how to compute ellipsoids. The first is the so-called maximum volume inscribed ellipsoid. Okay. Suppose that our set is a polyhedral or a polytop. Then a well-known result is that in order to find a quadratic, that an ellipse that is the maximum volume inscribed ellipsoid inside a feasible set, you have to solve this problem here. And this is, by the way, it's a tractable problem. Okay, so that's a maximum volume inscribed ellipsoid. I don't know if you have a picture here of one, or here it's this example. So the minimum in this example, the minimum is in this point. That's the minimum over the original set. Just computed from convex programming subject to this feasible set, and the furthest point on now in the ellipsoid on from that point. That's computed by the simple quadratic problem that I showed you. Turns out to be here. Okay, but this is not we can improve it. So we take the line from the minimum to the furthest point, and we continue it until it hits the feasible set, because we want to start phase 2 of the algorithm, the gradient ascent, from a feasible point. So this is the feasible point that this will be our x0 for the phase 2 algorithm. Okay, that's what. I'll go back to this picture because so this is if we have a polytope constraint set, then we have to solve this problem. What happened if you have many constraints, and not that was only for one linear constraint. If you have many linear quadratic constraint, then this is another well-known result. Then you have to solve actually this semi-definite programming problem. So using the maximum value inscribed by ellipsoid, you have to solve this problem. This limits in some way the size of the problem, the number of linear constraints we can use, and you will see it later. Okay, that's another way. Yeah, the other possibility is to approximate the feasible set by two ellipses based on the analytic center of the convex set X. There are two. One, the inscribed ellipsoid inside the feasible set, but you can also compute the circumcised, the one containing the feasible set. And this is done by solving this problem. And the result by Yar tells you that to find the inscribed ellipsoid, you have to, this is the quadratic that you have to add to solve. And if you want the circumcising ellipsoid, this is the problem that you have to solve. Here is an example of the two ellipsoid, the inscribed and the circumscribed ellipsoid. And again, suppose that the minimum of your problem, even the unconstrained one, is here. And this is the furthest point on the ellipsoid from this point by the Hessian distance we talked about, by solving the hidden convexity problem, is here. And then again, we continue the line and hit the boundary, not necessarily in an extreme point like here. Okay, and so this is our x0 from the phase 2, and then from phase 2, you will reach, in this example, this point, which is turn out to be the global maximum. Now, sometime approximating a feasible set, even in particular a polyhedral one, might not be a good idea. And here is an example. What happened? If you have a feasible set, here it's a polyhedral one, but it's very narrow. And suppose that your meaning point is at that point here. Since the ellipsoid cannot, and the optimal, the maximum of that particular example is here. But the furthest point from this point on the ellipsoid, because you cannot push it to that point too much, you'll find that the furthest point is on the other side, both for the inscribed and circumscribed ellipsoid. Very bad. So for this case, using the ellipsoid to approximate, well, a very narrow set like that one, it might not be a very good idea, or why not give you a satisfactory, and we'll see many numerical examples soon that actually, so what we do here, we have another approximation. We just approximate the feasible set by a box, just the box containing the feasible set. That's the one here in the green line. The furthest point now of the box from the minimum is this point here. In about 2 iterations, it will reach in phase 2 of this point here. So now we have 3 methods. The two methods based on the analytic center approximation, the method, the maximum value inscribed ellipsoid, the box uncertainty, and there is a third one, which is just a random start. So there's a special way how we generate the random in a way that, since you have the option to start a lot of random points because phase 2 is a very cheap algorithm. And usually if you have a good starting point, it will converge very quickly. So that will be the 4 methods we are talking about. And in the algorithm, finally, we use all of them. The algorithm use all of them and finally take the best result. So now maybe I will start with a few examples. This is example, maybe I will come to this example. Well, here we maximize, the feasible set is the intersection of three ellipsoids. The feasible set.
Sorry, Ronnie, can you zoom in a bit just to make it more visible? Can you zoom in a bit?
Any what?
Zoom in, like increase.
Yeah.
The plus, yeah. Thank you.
Okay, so you maximize this convex objective function. The feasible set is the intersection of 3 ellipsoids. And you see that, in fact, all the method in this case gave basically the same result. Random here actually gave a good point, but it cost in the time, because you have to generate a lot of starting point in order to get this optimal solution, or the one that it's the same as the other one. Look, that the maximum volume, the number of variable here is not too large, it's 25. So the maximum volume ellipsoid, which is you have to solve a semi-definite, is still doesn't ask for much time, and also the analytic center one, but the box is amazingly fast, and when it works, it's usually amazingly fast. So that's that example. Now, don't be so favorite of the random, because look happen when the dimension, this is the number of variables versus the computation time. For the analytic center, time grows quite moderately with the dimension, but for the random, it grows very widely. Beyond 400 or 600 variables, it becomes time-wise not very practical. Okay, now this is an example where some of the method, this is an example. This is, by the way, is an example which we solved with another global optimization method by Selvid and Hertog, myself, and forgot even the
Breckelmans.
Who?
Breckelmans.
Yeah, Breckelman from
yeah.
Tilburg. So this example was solved there, and we used the same one, and we got basically, when it works, we got the same result, but not for the analytics center, very bad here. And this is because in that example, you see that later the AC recovered, but when the dimension was still low, we got exactly the picture I showed you with a narrow ellipsoid. That ellipsoid based on narrow feasible set are not very good approximation of the feasible set. But the other method actually gave the best result. And all the other one gave it very quickly. Even for 200 and 240 variables, the time is very good. The algorithm is very fast. This example are taken from a paper by Enbat from 1996. The examples are problems that have what we call the simple function. So especially simple feasible set, either polyhedral, and you see the largest one has 150 variables. And the constraints are either linear, the objective function is linear, a kind of a norm. And if there is a non-linear, it's only one or two norm variables. So the rather simple non-convex set that has to maximize. And this is the result of Enbach. And look first on the bottom. All the method that we ran, including random, analytics center, and the two versions and the box, got exactly the same result as Enbach. That it's actually the global optimum. But in this example, all the analytic tree method that they designed give you the same result and quite fast, especially the box and the random. But look what happens to the random. That's the global. That's what the random give you when the number of variables become large. And you see it started to drift away. It gives you a much worse maximum than the global one that you can get. And it gets worse and worse as the dimension grows. Let me increase this one too. Here we solved a problem of minimizing I think it was a quadratic even, subject to constraints, linear constraint, with an integer variables. So why can we still solve such problem? What we do first is that we ignore the integer and we just take the feasible set of the original linear constraints without to approximate by the ellipse and so forth, and we solve the problem to get the starting point. Once we got the starting point, we go to phase 2. Phase 2 starts from this starting point, but phase 2, what is that? He solved a linear program. He solved the gradient times x minus x star. It's a linear program. Subject to a linear constraint, we say that there are linear constraints here. And now there are integer linear, and we solve an integer linear programming. So it's still tractable. And you can see this was the solution. Remember, at this particular point, the AC was bad, but the good solution were for the random and the box. And here it was 370. The computational time we got a very close solution with the integer. So without assuming integer, that was the solution. And then it became 370. Both for random and for box. Here it was with 100 variable. That was the continuous solution. And the max algorithm with the integer got 691 rather than 692, almost the same solution. So we know that this is a correct integer solution. So the merit is that maximizing a convex function subject to linear constraints with integer variable can be solved by the algorithm using the phase 1 and phase 2. So we also tried the problem with log sum exponent, a very well-known test function and appears a lot in application under all kind of ellipsoid constraint. That's actually a circle. Here is also some of the problem that we solved. Polyhedral with quadratic objective function, exponential, and also sum of max, intersection of 5 balls, and also intersection of 3 ellipsoids as a feasible set. All methods actually work very fast. Of course, when the dimension become too large, when the dimension become like 100, you see that random start to have time was great difficulty. If you give it enough time, it will solve the problem as well. But the R1 solve it in this case in a few seconds, not 150 seconds like here. So it's so as I say, the algorithm finally use all the. It doesn't use MVE actually in the what I call the benchmark algorithm. If the dimension is bigger than 25, we don't run this one. We run only the other 3. Okay, so this is what I have to say about the COMAX algorithm. But let me also mention something. There was and there is, at least on my side, a hope that once we have a way to solve a maximum convex function, we can try to go back and look at a much more difficult problem, which is minimize or maximize the difference of convex function. This is a problem for which I don't know how many hundred papers were written on. So the hope about 1985 from a paper by Riatu said, this problem can be converted to a maximum of convex function. Here is the problem. Call age t variable t, add this inequality. So this problem is equivalent to this problem, to the maximum of this problem. That should be maximum here, not minimum. So you can solve this problem. It's a convex function subject to convex constraints. So why this is irrelevant? Because there is no minimum here. The minimizing t goes to minus infinity. The whole idea of Comax cannot be used here. So this is still remain something which means that maybe can use Comax, and I think we know how to do it somehow, but you cannot apply it to just the fact that you can write the problem as a maximum convex. You need to be able to have a minimum and to be able to find it. And that problem, which is that problem, it doesn't satisfy that. It's a different level of difficulty. So maybe I should stop here, and I'll be happy to answer to any remarks or comments.
Thank you so much, Ronnie, for the nice presentation.